So, our last topic for light is analyzing what happens when multiple waves interact. So, you probably learned some of this, hopefully, in your 1401 class. You might have done a unit on waves and sound, and a lot of that is going to be very similar. So, whenever two waves interact, they add up with an algebraic sum of the waves. So basically, if you take every single point and add it between the two waves, that is where you get your resulting wave. We call that the superposition principle. So, for example, if I was to add this point and this point on those two waves, mathematically, if I take whatever their amplitude is, remember the amplitude is the size, and add them together, I'm going to get a wave that is twice as big as the original because they're lined up. If I take this point down here and this point down here, that's going to give me, since they're in phase with each other, that's going to give me a really big negative value. If I were to pick the points along the central axis, like this point here and this point here, those are both going to be 0. And so when I add those points, I still get 0. So if you take up every single point and add them together, you could make the resulting wave just through adding points together. It's a little tedious, but we do need to take into consideration the direction that they're moving, their amplitude, which is how tall the waves are, and whether they are in phase or out of phase. In phase meaning perfectly lining up. So whenever we are talking about the interaction of those waves, we call it interference. Now, interference kind of has a negative connotation, like it's always going to cause problems, but we could have constructive interference, which is interference that happens whenever the waves actually build upon each other. They are usually in phase, or at least some part of the waves are in phase, so that you get those larger peaks than we originally had to start with. So you're going to get something that is larger than the original wave. That's constructive interference. Now, if your waves are offset from each other, what's going to end up happening is that if you have your peaks of one wave near your valleys of the other wave, then those positives and negative values are going to cancel. Maybe not perfectly, but you're going to end up with waves that are smaller than either of the original waves. We call that destructive interference. They have a tendency to cancel out and make smaller waves. Of course, if they're exactly opposite of each other, they can cancel out to 0. Although that's really hard for real waves to do. So if you have perfectly constructive interference, then the waves are going to be perfectly in phase. If they are out of phase by a factor of pi, so they're offset because these are sinusoidal, so that's 180 degrees offset, then they're going to cancel out to 0. That's perfectly destructive interference. Most waves are somewhere in between purely constructive and purely destructive interference. So why would they interfere? Well, our light waves are bouncing off of everything. So if you were to have a mirror like we saw and you have a light ray from the source, some of those rays are going directly this way, some of them are going other directions, and if they bounce off of some mirrors, then they could end up on similar paths and therefore interact. But because they have different path lengths, they're going to have traveled different distances, which means their peaks are not necessarily going to perfectly line up anymore. So, for example, if it was an electric field wave, these vary in both space and time, and we're going to have a slight offset. Okay, so that offset that we're going to have, and I changed this to delta x instead of s. Sorry, I didn't change it here. You're going to have a path difference. Delta x is the difference in your path length. Constructive interference, that purely constructive, when you get that maximum amplitude that's possible from the interference, is always going to be based on some multiple of the wavelength, so m. So some multiple, that's got to be a whole number integer. So when our path difference, the difference between the distance that they've traveled, is a whole number multiple of the wavelength, that is constructive interference. Destructive, pure destructive interference is going to happen when they are offset. you're going to end up with 2m plus 1 times lambda over 2. So that's sometimes written differently, but the whole point is it differs by an odd multiple. Okay, so we have an odd multiple of a half wavelength. The reason it has to be odd is to get that 180 degrees offset. I often see this written a little bit differently. Sometimes I see this equation here written as, if you distribute that divided by 2 right here, is that would give you m plus a half times lambda. So I actually think that's the way it's written on your formula sheet. It's a little simpler form. So if you take a multiple of m and you add a half, that gives you your offset. So, but they have to be odd multiples. So real light waves interfere really differently than kind of our ideal sources. And this has to do with the idea of coherence. So to be coherent, the waves have to exist in the same time and space. And so what happens is that the differences in the wavelengths for a lot of the lights are such that they really don't interfere much. And real light comes like in short bursts, because if you think of like the way that light bulbs work, you know, they're flickering and all sorts of different things. So you get kind of these random jumps and phrases. So what we're going to do is we're going to work with like these ideal sources. And the ideal source we tend to use is laser light, because laser light produces these nice pure sinusoidal functions. They are also going to be laser light. We can limit it to a single wavelength, so a single color of light like red or blue or green, and that just has to do with the way that the light is emitted, is going to give us that kind of different ability to be able to get this nice pure version. So we don't tend to use light bulbs when we're studying interference of just like an incandescent style light bulb. We prefer something like a laser light that gives us one wavelength that exists the whole time. So there's different types of interference. So one type of interference is called thin film interference. So this is what gives you like the kind of the shimmer and the sheen, the rainbow effects, kind of like in bubbles or from like the oil slicks. And what ends up happening with thin film, if you think kind of like with a lens, you end up having like the light entering one surface, okay, the thin film, and part of it reflects and part of it refracts. The part that refracts then hits the next surface, and some of that is reflected and then refracts. Some of it is transmitted and refracts and bends through. So what ends up happening is that you're getting these different path lengths. So these light rays that are coming out are taking different paths. You're getting this interference that comes with that, which is what gives us those pretty rainbow colors. Because our rays that have gone the long path and reflected off of here before they come back up here travel a longer distance. Okay, so they're going to have that phase variance because of that distance. If they differ by a multiple of lambda, then you're going to get an increase in the amplitude of the waves. But if you have an exactly 180 degree or value of pi difference, then they are going to cancel out entirely. Most are going to be some combination in range in between. So what you can do is you could do some calculations for these. There are equations for thin film interference. I don't believe I put any of those on your homework because it's not really important to be able to do those exact calculations for our purposes. But when we use different wavelengths, they're going to tend to add constructively at different angles. So what happens is red light is going to refract differently than blue light. And so we're going to see different kind of those bands of colors because each color bends differently. We saw that with prisms. So the anti-reflective, anti-glare coatings, like if you get glasses and you get an anti-glare, or you have an anti-glare coating on like your car, those are using this idea that use that thin film interference so that we get a perfect balance of the incoming and the outgoing ray. So these two rays are exactly pi out of phase with each other. So then you end up with some cancellation there, to get rid of that glare, to get rid of that reflective glare. So it's kind of cool. Now, we'll spend a little more time with diffraction. So when a wave, we assume that we've got a wave that's coming out, and we assume that these are our crests. You might have seen sound waves represented this way. And our valleys would be the white in between. Okay. Then you're going to get your maximums and your minimums. So you've got these wave fronts that are coming out, and the wavelength would be the distance from crest to crest. Okay, that would be your wavelength. Oh, sorry, interfering with my buttons down there. Okay, so that would be our wavelength. Yeah, it doesn't like that. There we go. Okay, so that would be our wavelength for this wave. So what happens when they come across a boundary? So we've got a boundary here. They have to pass through this gap. Well, what we would think is that they would just keep on going. So it's like these block this here. But that is not actually what happens. That's not what we observe. That's not what you observe with sound. Because if you picture that our sound waves were coming this way, then if you were to stand here on the side of the wall, then you wouldn't be able to hear anything. But we know we can hear around corners. And that's because waves tend to diffract. They tend to bend around corners. So, this idea that as your waves pass through these gaps that they're completely blocked, yes, this is getting blocked here. But what happens is they don't just pass through, they spread as they move. And what we assume is that if our aperture, if our hole, our gap, is small compared to the wavelength, then what happens is we get a spherical wavefront. It almost acts like a point source, and it spreads out. Now it's going to be at a lower intensity than what their original was, because a lot of the wave has been blocked. But all waves are going to do this. So our sound waves do that. And this is part of what proved that light is a wave, is this ability to diffract, to spread when it passes through this aperture, this hole. So to see kind of how this works, I've got a PHYS simulation here. I decided not to do a lab specifically with this to save us some time. So I wanted to give you a chance to kind of see how this would have behaved interacted. So let's just look at a laser source. So that's what we have over here on the left is a laser source. So if I was just to turn on, right now it's set for a green light for our frequency. So we can assume that our light is a wave. And so these dark green areas, those are our crests. And the black areas at the center of the black area would be our troughs. So we've got our crests and we have our troughs. So we can see here what happens is that our point source spreads out 360 degrees in all directions. So we're getting these spherical wave fronts. And I can see that it gets dimmer the further it is, because intensity is an inverse square law, so it's going to decrease quickly with distance. Now, if I change the frequency, so I'm now having some sort of red light here. So I can see that my red light is generally not as bright as my green light, and that has to do with the fact that our energy is proportional to our frequency. So the higher the frequency, the brighter and more intense our light is also going to be because of the higher energy. So I can see that if I switch over here to like blue or violet. All right, so we can see that I get that brighter, more intense light kind of at the start. So here, what happens if I have a single slit? So I've got those planar wave fronts. So I've got this long plane wave, and I can see that it is spreading out, going through this single slit right here. I can see that it's most intense at the center, but I can see that I have light on the other side of the barriers because of that spherical diffraction pattern that we are getting. I can change like the width of the slit, and I can see how that kind of changes the behavior of my light. It changes the shape. I can put a screen up at the back, and I can see what would I see if I put a screen up there that could actually capture that light. And I see that I get this intense band at the center, and then it's less intense further away. So if I bring my slit closer together, give a chance for that light to hit the screen, I can see that I get a much, much smaller intensity of light, and you can really not really even see a lot of green light there at that point. But we're going to spend more time on double slit interference. So we're going to do 2 slits right here, because this gives us really cool interference patterns. So what we can see is we can see that we're getting these patterns of bright sections and dark sections, and those are constructive and destructive interference. So there are some points that are actually brighter than the light that's passing through, and some that is obviously darker. And we can see that we're getting these 3 different lines here, and we only had 1 line with 1 slit. So if I was to change, say, the width between the slits, okay, I can see that my pattern changes. As the width of those slits gets bigger, more light passes through, and I get brighter bands. Now, if I was to change the separation of the slits and keep those slits the same distance apart, what happens is my bands are going to broaden, and I can see that I get kind of this smaller section with bigger gaps kind of in between. If I make those slits smaller and see what happens, you can see they get dimmer, but I get more separation between each of those bands. And I can see that really cool diffraction pattern with that interference between the constructive and destructive interference sections. So kind of fun things you have going on there. So if you had a single slit, then what you would do is we would look at the spread. Our spread is given the variable theta, and it's approximately equal to the wavelength over A. A is the width of the slit. Okay, and that gives us the spread essentially of the peak. Okay, so from our maximum peak to our lower peak. And we get this kind of single peak here in the center, but you get these smaller peaks kind of out here. So Huggins first explained this property, and he pictured that each planar wave, so each of these long linear wavefronts, is actually not linear. They're made of a whole bunch of spherical wavefronts. So if you break each of the line into points, and of course you technically have all these points in between, but that'd be really difficult to draw, that each wave is actually a spherical point. And so then as it emanates and progresses, you're going to get more and more spread on that. And then what you are actually seeing is the leading edge of all of those little bits, which he called wavelet. So you can find that edge by adding them all up. But we can see that our behavior is going to be different at different points. So when you take that wave and you encounter an edge, the spherical wavefronts, if you picture it all, explains why there is a change in value. Because the wavefronts that don't get diffracted are going to be straight, but then we're going to get kind of this curved intensity, and then we get this kind of interference pattern on the side where our intensity gets bigger even though we're getting further away. So because that happens, we are going to have that spread. Eventually it's going to spread to the point where we won't be able to see it, and you won't be able to see the images at all. So as they spread, they're going to interfere and produce these are called fringes. Okay, this over here is called a fringe. So you're going to get this interference pattern, and eventually you're not going to get image. There's going to be too much interference. So as they spread, they're going to interfere, and you're going to get those fringes. So we have our double slit interference like I showed you before. So you picture that the wave that makes it through this thin slit, okay, remember these, it works best when the slits are going to be thin, because otherwise they get really broad. And then you're going to have your other wave come through. And what's going to happen is here, remember, our crests are drawn, our troughs are not. Our troughs are in between, exactly in the middle. So like this is constructive interference, constructive. Two maximums interacting with each other. And then here, halfway in between, you're going to also have constructive interference where a trough and a trough add up. But you're going to have some of these points where like your trough and your maximum interact. That's going to be your pure destructive interference. And that's where you get patterns that look like this. If you've ever looked at a pool or a body of water, you get these bright areas, and then you get these really dark areas. So the bright areas are your constructive interference. Your dark areas are your destructive interference. And you could see those patterns when we played around with the simulation. So if you were to put a screen over here, you're going to get your fringes when you trace the path of where those maximums end up going. And you're going to get your dark areas in between, where you're going to get exactly in between those areas, where you get the darkness, where they get them to cancel out. So what you end up getting is you get these peaks of intensity at those bright locations of constructive interference when you put your screen back. So Thomas Young used this double slit interference to prove that light was a wave. Einstein proved that light was a particle by using the photoelectric effect. Now, what we can do is we can actually predict the locations along a screen where we think that the dark fringes and the light fringes, the areas of destructive and constructive interference, should appear. So we can do that using some geometry. We have to do a little bit of an approximation because it's going to be close but not exact. You might have done this with two speakers making interference in your mechanics class if you did wave and sound. That was always an example that I did. Of course, I'm a musician, so any examples I could do with music were always awesome. So here, same idea. Instead of having two speakers, one here and one here, we have that light source, that planar wave that comes through here and then passes through and spreads out. Okay, and we're going to get that interference. So that's our setup. That's what we have going on. So D right here is going to be the distance between the centers of our slits. L is going to be the distance from where our slits are located to our screen. Y is going to be the distance from the center point between the slits to point P, where we're interested in. So if we want to figure out what's going on at point P, is it a bright fringe? Is it the brightest, largest amplitude, purely constructive interference? Or is it going to be purely destructive interference? Is it going to be a dark fringe? Or is it going to be somewhere in between? So we can actually use some geometry to make those predictions. So it's based on the path difference is what the interference is. So coming off of here from this slit, we have R1, which has a particular distance. R2, we can see, actually has to travel a further distance to get to that point. Now, really, we treat this as an absolute value, so it doesn't matter where along here it is that we're looking along the screen. It's just the difference in the path lengths that are formed. So we could actually make a triangle that shows those difference in path lengths. That triangle is here. So we have this right here, this distance. If you make a perpendicular projection right there, this distance right here, that is our delta x. Okay, that is our or delta r. I don't remember which way I have it on the formula sheet. It might be delta r. on the formula sheet. That's the difference in path lengths. So this is a 90-degree angle right here. So what we end up having is we have a right triangle where D is the hypotenuse. And we have our 90 degrees right there. So that difference is approximately D sine theta. So this right here would be that angle theta. So our delta R is going to be approximately D sine theta, because delta R is the opposite side of that triangle, and opposite's always based on sine theta. So what ends up happening is when we have that path distance, these are delta R. So when our delta R is equal to m lambda, okay, is equal to m lambda, lambda is our wavelength, our integer multiples, then then we would have an example of a bright fringe. Okay, so when our path distance is an, oh, I spelled integer wrong, I'm sorry, is an integer multiple of the wavelength, then we are going to have bright fringes. Now, if, on the other hand, our path difference is in between, so is exactly half a wavelength offset, that is going to give us pure destructive interference. Now, that's going to be true for our path lengths, but we don't always have those ability to measure those R's, because those R values, like those are going to be for different distances. It's a lot easier to use the physical construction of the separation distance L and Y. Okay, so that is always true. But what we tend to do is we tend to relate those then to these other dimensions, Y and L. So in order to do that, we need a second triangle. And it's actually a similar triangle. It's not exactly it, but it is really close enough for us to use an approximation. So here's the next triangle. We have a hypotenuse here that's actually approximately the average between R1 and R2. And then we have Y is this leg, or 90 degrees here, and RL is this distance right here. So this angle theta is approximately the same as the angle theta that we used here for this calculation. So L is the distance from our slits to the screen, and it is the adjacent side of this triangle. Y, which is our distance from our center point right here between the two slits to point P where we're interested in, is going to be the opposite side. So that means there's a tangent relationship. Tan theta is opposite Y over L. Now, as long as our Y is small, you could use an approximation, which you don't have to worry about, that when Y is small, sine theta and tan theta are approximately the same value, because if Y is very small, then it means you're going to have mostly an adjacent side of your triangle. So when that's true, you're going to end up with your tan theta being approximately Y over L. So when we combine those together, what we do is in our equations over here, we replace sine theta with tan theta, which is equal to Y over L. So that would give us D, replacing our sine theta with tan theta. And then instead replacing our tan theta with Y over L, so we get D Y over L. And that means we don't need to know anything about the angles. We can just find Y using those relationships. So these are delta R. So that's equal to delta R. So that's our distance in our path length. But we don't even really need our path length differences then, which is good. So I don't want to know what R1 and R2. I just want to be able to look at L and Y and figure out where along this screen it's going to be. So if I just use this side right here, m lambda, and my dy over L, I can rearrange those equations to look like this. So Y for a bright fringe is going to be m lambda L over D. Once again, just setting those two equal to each other and solving. And then our Y dark is going to be our m plus 1/2 lambda, and that's also equal to dy over L, rearranging to solve for Y. So the equations that you need on the formula sheet are these ones here. These guys are given for you. It doesn't tell you whether it's a bright fringe or a dark fringe. Those ones are there. What you need to remember is this triangle. So you need to remember this triangle. And then we've got our L and our Y. That one's not on the formula sheet for you. But just remember that our sine theta is approximately equal to Y over L. And then you'll be able to solve any problems with those formulas. So here's an example. We have light of wavelength lambda equal to 500 nanometers is incident on a double slit. So we've got our lambda, a wavelength that comes into our double slit. We have D is 50 micrometers. We want to know what is the fringe spacing on the screen 50 centimeters away. So fringe spacing is the difference from one bright to the next bright. So you're always going to get a bright spot in the dead center. And then you're going to have a dark spot. And then you're going to have a bright spot. So what we're really looking for is we're looking for delta Y. But we can use the first bright spot. This one's going to be M equals 0. So that's going to how we're going to use this. The first bright spot after the central axis is M equals 1. So what ends up happening is if I was to find those bright spots, I would find my Y for this one. And delta Y is essentially Y minus 0. So that Y is going to give us my fringe spacing. And so that next fringe is actually the same distance. There'll be a dark fringe and there will be a bright fringe. That would be M equals 2. Or you could do delta Y is going to be the difference between M1 and M2. Those are going to be equally spaced. Okay, they form that even pattern. We saw that on the simulation. So we've got L, which is 50 centimeters. So we have to look at our equations. For our bright fringes, D sine theta was equal to M times lambda. That one's on the formula sheet. We also know that we have a triangle. This is the one you have to remember. That if you were to create a triangle to that first fringe right there, that first bright spot, okay, that's basically point P that we were talking about before. So that is our Y value right here, and then we have L. And then we have our angle theta. So we said that for that angle theta, that triangle is tan theta would equal Y over L. But we said that was approximately the same thing as sine theta. So that means we can replace the sine theta with Y over L. We're just using 1 because we're looking for the first fringe. And that's going to equal lambda for our wavelength. So since we're looking for Y, I'm going to multiply the L to the other side and divide by D. So I get Y is equal to lambda L over D. And at that point, it's just a matter of unit conversions and plugging in. So our wavelength is in nanometers. So we have 500 nanometers. That is going to be times 10 to the negative 9th meters. Nanos times 10 to the negative 9th. And our L is 50 micrometers. Micro is 10 to the negative 6. So L is going to be, oh, wait, hold on. Oh, that's D. Sorry. L is 50 centimeters. Sorry, my bad. So that's going to be 50 times 10 to the negative 2 from centimeters to meters, divided by my D, which is 50 times 10 to the negative 6th. And you can plug that in, but we can also see this simplifies kind of nicely. The 50s are going to cancel out here. 10 to the negative 2 is going to partially cancel down here to the 10 to the negative 4th. And then we have 10 to the negative 9th and 10 to the negative 4th. So that's also going to partially cancel to 10 to the negative 5th. It's going to cancel here. So really what we're left with is 500 times 10 to the negative 5th. But we have 2 more zeros here, which cancels right here. So that's 10 to the negative 3. So we get 5 times 10 to the negative 3 meters, which is the same thing as 5 millimeters. So we're going to get a bright fringe every 5 millimeters. So here at 0, we have one here at 0 millimeters. We'd have 5 millimeters. We'd have 10 millimeters for the bright fringes. We could do the same thing with the dark fringes if we wanted to find the dark fringes. What would end up happening is if I was to try and use the dark fringe formula, that's d sine theta is equal to m plus a half. Sorry, I've got a little bit of a delay right here. Times lambda. So our m is still based on our bright fringes. So m is still equal to 0 for this first dark fringe. So that would actually be 0. So we would do d sine theta is equal to 1/2 lambda, but we're also going to replace our sine theta with y over L. So we would get dy over L is equal to 1/2 of lambda. So if I wanted to find where's that first dark fringe, what I would do is I would solve for y. So to do that, I would get y is 1/2 of lambda times L over d. And I can see that if I was to plug in values, that would end up being 2.5 millimeters. And that tells me that my dark fringe here would be at 2.5 millimeters. Now, what you have to be careful of is that my next dark fringe is not at 5. That's why it said odd multiples. It said odd multiples, because if I double that, that actually gives me my bright fringe. So then my next m would actually be not at the next one, would be the one after that.